8.3 Ionization of water. Now this section helps us understand a little bit more when we go to the next section when we're determining pH and where that equation is coming from. So let's see what we're talking about. We're really talking about what happens when water forms ions. Okay, so in a neutral solution, our hydronium ion concentration, these brackets mean concentration, and our hydroxide ion concentration, brackets mean concentration, they're equal. We have equal amounts of hydronium ions and hydroxide ions if the solution is neutral. But in an acidic solution, the hydronium ion concentration is greater than the hydroxide. You know, this acid is greater than the base. Well, of course, it's an acidic solution. So in a base solution, the hydroxide ion concentration is greater than the hydronium ion concentration, which does make sense once you know what these kind of represent. Now in water, a hydrogen ion is transferred from one water molecule to another. So when water is just sitting there in a glass, it's not really just sitting there in a glass. One molecule of water can act like an acid and donate a hydrogen, and another molecule of water can act like a base and accept a hydrogen. And in so doing, you will notice when one of our waters accepts a hydrogen, then we have our hydronium ion, and when the other water has donated its hydrogen, we have our hydroxide ion. Well, we're going to have equal amounts of those. So in a neutral solution of water, we're going to have equal amounts of our hydronium ion and our hydroxide ion. Now you may go, oh my goodness, so water's doing that. Well, no, remember, well, yes, but not a lot. Remember when we have these frontwards and backward arrows, equilibrium, that means that it doesn't all go to completion, that some of it happens and some of it is going to be on the left-hand side. So the question is how much? Well, at 25 degrees Celsius, this is 1 times 10 to the negative 7 value. In other words, 0.000001. That's how much it happens. Well, that's not a whole lot. However, it's enough to influence and to help us create this equation. So in pure water, what I was just mentioning, the ionization of water molecules produces small 0.000001 amounts of hydronium ion and hydroxide ion concentrations. So those concentrations are indicated in brackets. And so in pure water, our hydronium ion concentration is 1 times 10 to the minus 7 molarity, and our hydroxide ion, the concentration is 1.0 times 10 to the minus 7 molarity. Notice they're equal concentrations. Molarity means concentration, they're equal concentration. So, of course, it's going to then be neutral. All right. However, when we add acid to pure water, the acid, because it donates a hydrogen, is going to increase the amount of the hydronium ion. And so it causes the amount of the hydronium ion to get bigger. So that means to get like something to the negative 6 or negative 5 or negative 4 or negative 3. All right? And in so doing, we're going to decrease the OH concentration. So in an acidic solution, our hydronium ion concentration is greater than our hydroxide ion concentration. If we were to add a base to pure water, we're going to have more of the OH ions, those hydroxide ions, which then is going to decrease the hydronium ion concentration. It causes the OH ions, the hydroxide concentration, to get bigger, i.e., like to the negative 6 or negative 5 or negative 4, you're going to have greater. So in a base solution, we're going to have more hydroxide ion than our hydronium ion concentration. So just to compare, let's make sure we remember that in an acidic solution, if we have more acid than base, it's going to be acid solution. Of course, the hydronium ion concentration greater than a hydroxide concentration, we're going to be an acidic solution. If those concentrations are the same, it's neutral. And if we have more hydroxide ions than hydronium ions, it is a basic solution or alkaline solution, or called a base, however you want to say that. Now, this constant is considered, they have this symbol K for constant, and this water, so Kw, the ion product constant, Kw, K for constant, W for water, it is the product of the concentrations of the hydronium ion and the hydroxide ion. So write this formula down. Our Kw equals our hydronium ion concentration times our hydroxide ion concentration. And we get these values from the concentrations in pure water, which is, in pure water, when it's neutral, our hydronium ion concentration is 1 times 10 to the minus 7 molar, and our hydroxide ion is 1 times 10 to the negative 7 molar. So when we multiply those together, we're going to get that the ionization constant of water is 1.0 times 10 to the negative 14. So when you look at our different examples of our hydronium ion and our hydroxide ion concentration in acidic, neutral, or basic solutions, you'll notice the Kw didn't change, but when you change the hydronium ion concentration, you will notice what's going to happen to the OH concentration. So as we get our concentration of hydronium ions is greater, our solution is going to be acidic. If our concentration of hydroxide ions become greater, then it's going to become a base solution. So now then, get your calculators out, and please make sure you practice how to do this. Because if you don't know how to do this, please send me an email and let me help you work this through your calculator. So, the guide to calculating the hydronium ion concentration and hydroxide ion concentration in aqueous solution. First, write down our formula, Kw for the water, so that we can solve for it. So Kw equals our hydronium ion concentration times our hydroxide concentration, which is 1 times 10 to the negative 14. So then we substitute in the known, whatever they give us, whether it's the hydronium ion concentration or the hydroxide, and then we're going to calculate. So, what is the hydronium ion concentration of a solution if the hydroxide ion concentration is 5.0 times 10 to the negative 8? So we first write our Kw. So our hydronium ion concentration times our hydroxide ion concentration is 1.0 times 10 to the negative 14. Now that is an equation you should be writing down and have on your formula sheet. So now, since they ask for the hydronium ion, we need to get the hydronium ion all by itself. So we do that by rearranging our formula, and we're going to divide through by OH on both sides. So you'll notice then that our hydronium ion concentration equals 1.0 times 10 to the negative 14 over the hydroxide ion concentration. So when we plug those values in, it is 1.0 times 10 to the negative 14 over 5.0 times 10 to the negative 8. When you do that math, you should get 2.0 times 10 to the negative 7. If you don't, you're probably pressing your times and your multiplying key, and you're plugging in 10 and negative 14. So make sure you're not doing it that way. If you do not get 2.0 times 10 to the negative 7, then try it again to try to get that. If not, please send me a message so I can help walk you through your calculator. If lemon juice has a hydronium ion concentration of 2 times 10 to the negative 3 molar, what is the hydroxide ion concentration of the solution? Press pause and see if you can do this problem. So the first step is we're going to write the ionization constant for water. Our hydronium ion concentration times our hydroxide ion concentration equals 1.0 times 10 to the negative 14. We're going to plug in our hydronium ion concentration value because we are solving for our OH, so that means we're going to divide through by our hydronium ion. So we're going to go 1.0 times 10 to the negative 14 divided by 2 times 10 to the negative 3, and when you do that math, you're going to get 5 times 10 to the negative 12 molar. So please make sure you get that when you divide it through. So let's practice another one. The OH, the hydroxide ion concentration of an ammonia solution, is 4.0 times 10 to the negative 2 molar. What is the hydronium ion concentration of the solution? Press pause, see if you can do this. So we are going to write our Kw formula, our ionization constant formula, which is our hydronium ion times our hydroxide ion, equals 1.0 times 10 to the negative 4. Now we are going to rearrange to solve for our hydronium ion concentration. So we're going to put it all by itself. We're going to divide through by our OH on both sides. So when we do, we have that our hydronium ion concentration is 1.0 times 10 to the negative 14 over our hydroxide concentration, which is 4.0 times 10 to the negative 2. When we get that, we see that our hydronium ion concentration is 2.5 times 10 to the negative 13.